do that? Oh yeah, sorry. Yeah, I should have asked before.
No
are you happy to be recorded? I don't know if Thomas has asked already.
I'm happy as long as nobody laughs at me too much.
Okay. All right. Well, then we'll go ahead and record. And hopefully everybody's aware that we're recorded as well. All right. Well, I'm going to introduce Stephon. This is quite a list of things, actually. So very impressive. So Stephon is, many of you will know him. He's been in the business for quite some time now. He had his PhD in Brown all the way back in the year 2000. Then he did a postdoc in Imperial, which is when I first came across him, although I don't think he probably remembers that. It was at a school in Imperial one summer. Then he went to another postdoc at SLAC before becoming faculty at various places, Penn State, Haverford College, where I believe he did his undergraduate, Dartmouth, and now, of course, at a very prestigious institution at Brown. I think very broadly, I would say that Stephon works on quantum cosmology. I think that's probably the fairest description of his research. He's made really important contributions and, of course, won awards for that work, including, for example, an NSF Career Award, but there's many more. You could go through the list. But perhaps what makes him most impressive, I would say, is on top of all that great track record of research, which any of us would be proud of, is all the stuff he's done on top of that, which is really impressive as well. He's an accomplished musician. He's written, a fantastic book about the jazz of physics, linking, sort of music with maths and physics. He's an accomplished saxophonist. He's worked with people like Brian Eno. I remember we were at a conference once, and the jazz musician Stanley Jordan was there. That me and Stephon spent a lot of time hanging out with. That was pretty cool. I think Stephon was probably extra excited about that when that was happening. And on top of all of that, he's also the president of the National Society of Black Physicists and all the great work that they do. So a truly, multi-talented, doing so much for the community. And yeah, we're lucky to have him give us a talk. So I think at that point, we should pass over to Stephon.
So, well, all I'm saying is I'm deeply embarrassed and humbled because, some of my favorite papers in my career have come from people at Nottingham, and I don't even want to go into all those amazing work that you have done over the years. I've definitely gained from that, and also I want to just also say that it was a very I don't know what the word lucky moment for me that I did my postdoc in the UK. It was where I really, was able to find my, I don't know what the word is, find my vibe, for lack of a better word. And it was a very important stage of my career, and it always, so, UK physics always has a special place in my heart. So I could not, I couldn't resist accepting this. And to let you know, I actually skipped another meeting, not to make anybody feel, bad or anything. This is a great pleasure. Now, the talk is kind of pitched more in a hybrid seminar style, colloquium style. I will do my best to articulate, the ideas. So let's just begin. I knew there was one more thing. Antonio, I'm really enjoying your new book. It's a great work, and look forward to it, selling a lot and also winning some award as it deserves.
Great.
Okay, so
Stephon, you're muted. Just going to unmute you.
Can you hear me now?
Yeah, we can hear you now. That's good.
Did you hear what I said before?
After plugging my book, then I think we didn't hear anything after that. I think the gremlins decided they weren't happy with that, so they muted you. So everything from that point, basically, we didn't hear.
Did you hear what I said about my time in the UK?
Yes, we did hear all that.
Okay, that's the most important part. Okay,
good.
So I kind of want to couch my talk, and this is a perspective I have now, and my perspective has changed over the last 17 years. Working in 11-dimensional, from being a person working in 11-dimensional supergravity and cosmology, string cosmology, and I still pay attention to all those things. You know, consider myself a broadly defined theorist. But, you know, and so this is where I'm at now. So I want to kind of couch my talk on three mysteries. What is the origin of cosmic structure? What is the identity and the character of dark matter? Why is there more matter than antimatter? These are three mysteries I want to try to get at today. And let me kind of, you know, give you a forewarning. I may not get through the entire talk, okay? So, and that's okay. If I end up talking about two of these things or one, I think I'm going to get my point across. But my main point is, are these mysteries pointed to a common cause? So to give us some context here, let's consider something, a lesson, a very important lesson that we theorists should have learned or should learn, which was that despite our prejudices, experimentalists went looking for parity violation anyway in the weak interaction. And again, and despite our presumption that that the weak interaction should be parity conserving, they discovered that it was maximally parity violating. And the lesson here is the link between chirality and parity violation. So what we're looking at here is, to the left of a mirror, a chiral interaction, meaning that a left-handed W boson interacts with only left-handed fermionic states, in this case, leptons, and an up and a down quark that undergoes a transition, emitting an electron and a neutrino, and a parity reflection of that chiral interaction, which reverses the chirality. And the statement of parity violation is that that other chiral state is 100% missing. The right-handed interactions are 100% missing. And my goal today is to kind of revisit what we know. Wait. Before I go on, I'm going to skip that slide. What I want to now say is, if we look at what we know, what do we know in terms of theoretical physics? Well, we know that modulo the cosmological constant problem and the dark matter problem, general relativity is the correct theory of gravity, modulo those two problems. And I don't want to get into the precision tests and that kind of stuff in the interest of time. We also know that the standard model, up to the scales, the energy scales that we have probed it at the LHC, is also the correct effective field theory of the other three interactions. And we can ask the question, what do they share in common in terms of the principles? And what do they not share in common in terms of the principle? And I know that many of y'all, especially at Nottingham and in the UK physics community, have thought definitely a lot more about this than I have. So let's begin with that. They both share invariance principles in common. At the level of the gauge theories, at the standard model, it shares the principles underlying that, of course, gauge invariance principles. And at the level of general relativity, it's diffeomorphism invariance. So, but underneath that, we still have symmetry principles that guide the construction and the behavior of these theories. But the one thing the standard model has that general relativity doesn't have is chirality. And so the question I'm going to ask today is, what if we were to try to make general relativity closer to the standard model in terms of this principle, by endowing, modifying general relativity to have chirality, and ask whether or not such a theory could actually address these or intertwine these three problems that I'm talking about. Now, I'm going to ask for a 1-minute break so that I can just quickly grab a cup of water. Is that okay? We can go and pause.
Go ahead. Yeah, no worries.
Oh, thank you. Okay, that's much better. All right, so let me give you my pitch. Observations, and again, these the dark matter, dark energy problem, and other anomalies suggest that GR might need to be modified. And if this modification is parity violation, I'm going to show that there will be observational consequences for cosmology and particle physics. And we're going to actually explore a particular theory. It's certainly not the only theory. I know that the community is working on other approaches. This is just more of a, I would like to say an exercise in terms of what it looks like, once we violate parity in general relativity. And, nonetheless, I'm going to argue that this theory has been a useful tool to analyze how to tease out observations from modified theories of gravity in general. So obviously, the theory I'm going to talk about is called Chern-Simons gravity. And let me just show you the theory. What we're looking at is the action to the upper right-hand corner there. It contains the usual Einstein-Hilbert term. Could you see my mouse?
Yeah, we can see the mouse.
Okay, very good. Really, I thought it's an arrow. Okay.
Yeah, it's an arrow.
Anyway, I don't want to waste time. I was going to tell a corny joke, but and we have this, something like a pseudo-scalar field that I'm calling theta, and this Pontryagin density, R dual, which is analogous, sort of like an instanton number, FF dual in Yang-Mills theory, and of course a kinetic term. And this sort of naive, simple-looking theory, and of course I'm going to talk about how it's motivated from fundamental theory if one cares. We can think of it as an effective field theory. And I'll say more about that in the next slide. But this naive-looking theory actually has very interesting field equations. I mean, if you look downstairs here, we have a modified Einstein equations where the modification is this cotton-like tensor, cotton-York-like tensor, the CAB, which involves gradients of the Riemann curvature tensor in its dual. And this is where this parity violation, as I'll show you, is encoded in general relativity. We also have a field equation where a non-vanishing sort of Pontryagin density could source actually scalar waves of this scalar density. So we have a nonlinear system governing actually, this modification of general relativity. So that's the theory. Now, back in the days when I motivated this theory, me and Roman Jakiev and Mark Kamiankowski and collaborators, and my early paper with Michael Peskin and Mohammed Sheikh Jabari, we knew that we tried to motivate this from the perspective of string theory, where this term is necessary from a Green-Schwarz anomaly canceling mechanism. So we need this term actually, these so-called Chern-Simons terms. This actually ascends from the antisymmetric 2 form in string theory, and sometimes we call this a universal axion, or many axions can actually source such a term, and that term is actually necessary, but it's highly suppressed. It's volume suppressed, it's Planck suppressed, or string scale suppressed. So you would think that this term actually would actually not have a lot of important consequences. But as we'll see in the next slide, that's not necessarily the case. We could also get this term, as was shown in the paper by Greg Abadadze, Nico Yunez, my student, Leah Jenks, who's now a postdoc at University of Chicago with Wayne Hu. And then a recent paper by me and Cyril Krek-Sarbanowski, that we can actually get this from an effect from a UV complete theory of fermions coupled to a complex scalar, where the scalar field gets a mass. And when we integrate out a graviton in this fermion loop, we also induce this term. And as we see that the symmetry Bacon scale will set actually the scale this so-called suppression scale in RR dual. So this alpha, which I can call 1 over the scale of symmetry breaking, can actually be as small as, electron volt. And, just based on having some light scalars that are integrated out. So you can look at that paper. My point is that this type of theory can be seen coming from some UV complete fermionic effective field theory or from string theory. There are many motivations, or we could just simply claim it's an effective field theory up to some scale, some cutoff scale. And below that cutoff scale, this is the term we have. So that's a theory. And now what I want to do is actually explore sort of, what the sort of solutions of this theory in the realm of cosmology and astrophysics in terms of like black hole physics and gravitational wave physics. What do we see? Now, let me see if I have a slide that actually just gets to the point here. So instead of, let me just get to the point here. The point here is that if I take Chern-Simons gravity and I linearize it, and I now look at tensor perturbations, or gravitational waves in a specific gauge, in this case, transverse traceless gauge, the difference, and this is an important distinction that I want us to have in the back of our head as we move forward, so that we don't get lost in the jungle here. Even though I do like getting lost in the jungle. In Tobago, not Trinidad. There's snakes in Trinidad. Tobago has no snakes. Just keep that in mind if you ever go visit. Now, the key point here is that if I look at the vacuum Einstein equations, we know very well when T mu nu is equal to 0, box H left is equal to 0, and box H right, the wave right, is equal to 0. But in Chern-Simons gravity, that is not the case in vacuum. In vacuum, box H left is equal to a source, and notice that it's source with an imaginary, with an I there, which means that plane wave solutions will either be exponentially growing or exponentially decaying. And what we find is that generically, left-handed and right-handed circularly polarized gravitational wave in Chern-Simons gravity will be amplified relative to the other-handedness. So one-handedness will be amplified and the other-handedness will attenuate. And that is the source of parity violation in the sense that if I take a parity transform of left to right, it will not be equal anymore. All right, so that's the key thing. So what we find is that generically, when we look at just generic solutions in Chern-Simons gravity, this is a pattern that we find. We find for rotating black holes, we see a similar situation. We find in different, in inflationary situations, you find this pattern, and that's a take home.
Stephon,
so now let's talk about what impact this has for things like inflation and baryogenesis.
Stephon, what was the capital theta?
Huh?
What was the capital theta in that last slide?
Thank you. Yeah, capital theta is related to the velocity of the of this axion field, rescaled by some parameter that I'm forgetting. Okay, some dimensional parameter to make it dimensionless.
Okay.
And as we'll see, it's related to the rolling of the inflaton field in the context of inflation. Okay, so the first thing I want to talk about is, of course, the baryogenesis problem. And what I want to do is kind of like clarify, that I am considering baryogenesis that can take place either during inflation all the way through reheating. All right. So again, it's plausible that baryogenesis could take place after that up to the electroweak phase transition. I'm considering baryogenesis mechanism for that because I'm biased, since inflation is the paradigm that an accepted paradigm that explains the origin of structure or the seeds of structure. I would like to conflate the origins of the seeds of structure along with the generation of the asymmetry of that structure of the seeds. And so we understand how that works. Let me see if I missed a slide here. So just to say that baryogenesis are, one of the reasons why I'm motivated to do this is that baryogenesis mechanisms are usually, you can write a theory down, but how do you actually test such a theory? How do you test something that happened in the early universe? And you should definitely invite Chiral to give a seminar about a model that he and others are working on, using actually such theories like Chern-Simons gravity and new probes such as a trispectrum to actually put constraints on models of baryogenesis like this one. So that's one motivation. My motivation to talk about baryogenesis in the context of Chern-Simons gravity is to use inflation as a benchmark and also give a proof of principle that we can actually find clever ways of testing models of baryogenesis. That's the motivation. So we understand that basically the game of inflation, if you look to the vertical axis, which is time, and we have a physical scale on the horizontal axis, during inflation, the Hubble radius remains roughly constant in an idealized inflationary scenario. And we know that modes are created in the UV, and they basically get stretched out in the to superhorizon states, freeze, and re-enter the horizon as classical nearly scale invariant perturbations. And these perturbations source the curvature perturbations, which give us the anisotropies that we see on large scales in the CMB. And what we want to do is revisit the tensor perturbation. So the idea here is that the tensor perturbations come for free. And we want to ask, could there be an observational consequence? And obviously, since Chern-Simons gravity is at work here, and since I already gave away the hook that we're going to get something like parity violation in the gravitational wave spectra, what are the consequences for baryogenesis? So what I'm going to now show is that it is possible that a lepton asymmetry can actually build up during inflation and override the dilution. Sorry, my brain is a bit cloudy, so I'm really, struggling to be clear. But I'm sure that many of us have had similar situations, post-pub and anyway, so. So the point here is that during inflation, it is possible to generate an asymmetry, but we need to produce leptons that actually eventually are going to be interconverted into baryons through an electroweak phase transition at some later time. So let me give away the mechanism. I'll tell you what the mechanism is, and then I'm gonna try to substantiate it with some equations. The idea is straightforward, and let me just tell you that there are these Sakharov conditions that are necessary to actually generate a lepton or baryon asymmetry. We need all working at the same time, though they may come from different sectors of fundamental physics. We need a baryon or lepton violating process that goes beyond the vacuum structure of our standard model. So we need something like a baryon current or a leptonic current to be violated. We need, while that is happening, a biasing of baryons over antibaryons or leptons over anti-leptons, and that's charge conjugation and parity violation needs to be in place while baryon number is being violated to bias the production of matter over antimatter. And this has to happen out of equilibrium because the system will equilibrate and you'll end up washing out the asymmetry. So there are all sorts of mechanisms that have come on the table. This mechanism we find to be very, I don't know what the word is, simple, elegant, whatever the word is, dumb. And the idea here is the beautiful thing about inflation is that within a Hubble radius, the initial conditions of the inflaton field transfers its properties, right, into the mode creation and all that stuff. So we're saying, well, let's imagine that the initial condition for inflation, the inflaton itself, the rolling of the inflaton, the slow roll condition, what we'll discover is that it will source through this Pontryagin density and its interaction with the Einstein-Hilbert term, it will source a biased production of left versus right-handed gravitational wave. Now, the amplification of inflation itself, of course, will amplify those gravitational waves. And that sourcing is a form of CP violation. The CP violation in the inflaton field transfers itself into a CP violation in the production of left and right-handed gravitational waves. So that's one of the Sakharov condition. But what we'll show is that that CP violation immediately transfers itself into baryon number violation. And that's because of another thing called a gravitational anomaly, which is separate from the Chern-Simons gravity theory. So we'll talk about that. And the rapid expansion of inflation is already an out of equilibrium process. So the onset of inflation itself, making use of Chern-Simons gravity, will provide a very economical mechanism of leptogenesis. So now let's actually demonstrate this. So the first thing we need to do, let me just go backwards and talk about lepton violation. So the standard model has in it a gravitational anomaly. Now, the gravitational anomaly vanishes because the standard model is considered in Minkowski space. And you see this RR dual term here, which is analogous to the FF dual for the gauge anomalies. This is a global anomaly. This is an anomaly in the B minus L sector of the standard model. And it is non-vanishing. It is vanishing in Minkowski space. But of course, when this is non-vanishing, meaning when this RR dual is non-vanishing, you could generate a non-vanishing leptonic current. That's the first observation. But you also need an imbalance of right versus left-handed leptonic species. And in the standard model, that is the case if you're considering active neutrinos. We have 3 left-handed neutrino states. I'm not considering, I'm working below a scale of a heavy right-handed neutrino. Okay, so this R minus L, right minus left-handed state, is actually 3 in the standard model. So if this is non-vanishing, there's a potential to have a non-vanishing lepton number. And the question is, in the context of inflation, where the Chern-Simons gravity is replacing ordinary general relativity, what are the consequences here? Well, the first thing we have to do is to compute that RR tilde. So what we do is go back and revisit. We go back and look at perturbations during inflation, and we look at our tensor perturbations. And as I already showed you before, the equations of motion for the left and right-handed movers are sourced in the following way. If you unpack that equation, it has the usual form. I mean, if you set this equal to 0, you get the usual scale invariant power spectrum for gravitational waves that source the B modes. But in this case, it'll be sourced in the following way. And the idea here is that these gravitational waves are the things that source a non-vanishing RR dual. So we can compute the total lepton number produced during inflation, the entirety of inflation. And if you compute this and you get that the number of baryons, this is assuming, of course, that these baryons get converted into leptons by a factor of like, 1/3 or something like that. Oh, I forgot to tell you that the number we need is the baryon, remember, divided by the number of photons at last scattering to be 10 to the minus 10. So that's the number we're going after. And that's a redshift independent number. So once we've established that number, it remains that number. So if you go and you look at the paper and look at the details of that calculation, let me just say that the number depends on Hubble over M Planck, the number of species, of fermionic species in the standard model. And of course, this theta field that I told you, which is related to the slow roll parameter of inflation, and this cutoff scale. And notice that this cutoff scale is, right? It's important that this cutoff scale is below the scale of the effective field theory. So the effective field theory, we're assuming to be below 10 to the 16 JeV. And what I'm saying is that now this accommodates 10 to the minus 10. We have to be careful about that, and we can, if there's time, we can talk about the validity of this as an effective field theory and all that good stuff. But the point here is there have been follow-up work showing that actually there's a larger parameter space, because remember what I'm telling you here is that this is the number of leptons produced, the lepton asymmetry produced during inflation. And of course, this answer depends on the reheat, the sort of, the reheating mechanism. But as shown by colleagues here, Adhead and Long and Robert Caldwell, DeVolder, and others, that there's actually a lot of room for the reheat temperature, going from 10 to the 10 to the 10 to 10 to the 15 JeV, and to accommodate this baryon asymmetry index. So this model works for a very wide range of reheat temperature. And another slide showing that actually that if you have parity violating gravitational waves, you get an order of magnitude power spectrum. The black actually here is a power spectrum, B mode power spectrum signal compared to parity non-violating B modes. So there's a distinct feature. So this is just to show that, these models are things that could accommodate models of baryogenesis. And this is one of the things that theories that modify, that, violate parity in general relativity can potentially do for us. Chern-Simons gravity being one model. Let me add another thing here. You can also add gauge, sort of FF dual terms as well. And what people like Rob Caldwell and his colleagues have shown is that you can enhance the baryogenesis mechanism. It doesn't purely have to be pure Chern-Simons gravity. In follow-up work with a grad student of mine and Nico Yunez, we showed that, and Evan McDonald, we showed that actually this mechanism persists, that during reheating, parametric amplification could actually lead to even more exponential production of these left-handed gravitational waves, accommodating a lower energy scale actually for the Chern-Simons coupling. So we can look at that paper.
Sorry, can I ask a question?
Yeah, feel free to ask questions.
Yeah, I think on the maybe 2 slides back, I think when you talk about the B mode, so how can the power spectrum be comparable in size? Because don't you really have to treat this Chern-Simons term as a small correction to GR? I mean, shouldn't there be a hierarchy between the 2 power spectrum?
Yeah, so I think that this power spectrum is yeah, this yeah, so this is assuming that's right, a particular coupling that I can't recall right now for this parity violation term.
Isn't it just the theta r tilde?
Exactly, that's what that's what I'm calling the coupling, yeah.
Okay.
So I would say this is like what I would call a, what's the word for this? There's a word for this, an optimistic, an optimistic fit, okay, for parity violation. Okay, so let's now move into some work on Kerr black holes. So so it was shown by Younes and Pretorius that again, vacuum Chern-Simons gravity does modify a rotating Kerr black hole in the following way. And basically it induces a correction to, it does create scalar here, meaning that there is a profile, a non-vanishing radially fall off of scalar here, and also scalar waves as well, dipole radiation, for a rotating black hole. And remember, the no-hair theorem applies to Einstein's theory of general relativity, and this Chern-Simons gravity evades that. So you have the scalar here. And this is work, of course, that was done a long time ago by Nemanja Kaliper and Keith Olive and others as well. So apologies for not citing that, just to make that clear, and I will correct that in the future. And so what this leads to is a modification of the metric. So this DSK is a pure Kerr black hole metric, and this is a correction of the line element in the angular direction about the equator. Now, this is a slowly rotating solution, and this solution was shown to be modified in the rapidly rotating case numerically. So let's consider what the observational consequences are for in a black hole situation. Well, first thing that happens is there is superradiance in as well for Chern-Simons modified Kerr black holes. But there's also an interesting situation where what we call Chern-Simons caps, which are at the north and the south pole, we find that the focusing theorem does not hold, but there are no sicknesses associated with that. So what we see is that geodesics actually will actually get defocused, and it leads basically to some interesting phenomenon, such as breaking isospectrality between the polar and axial gravitational perturbations. And that's a much longer conversation. I invite you to invite Leah Jenks to give a talk on that. I just want to kind of highlight this event, this paper. So now let's talk about, spend some time talking about binaries. So this is just my little slide to show that in general relativity for a binary system would lead to this power law, this fall off of frequency to the 7/6, sorry, to the 3/8 power. And what Chern-Simons is going to do is modify the phase of these of the in spiral, actually in the and a very long, not long, but there's a word for this. There's a word for this. Not in the in the early phases of the in spiral. My brain is not, it's starting to not work, but thanks. So I'm going to skip this slide. This slide has to do with some earlier work that was done by Nico and I where we showed that basically another thing that the parity violation does, it changes the deflection angle of a binary system. And that's again, another line of work that hopefully you can take some interest in and look at these papers. Some follow-up work by Masha Kova and Will Farr and Stein and Issy. So what we're going to focus on is this initial stages of the end spiral and ask, what are the manifestations of a parity violating theory in the outer phases of this end spiral? Okay, so this is like a little picture of what the strain looks like in the early stages, and basically, as you get into the nonlinear regime. All right, so the first statement is that if you look at this picture here, everything is contained in this picture. So what we have are two black holes, not three. That's meant to animate the two black holes going around in an orbit. So we have two modified Kerr black holes, and there's scalar here. And remember, these scalar hairs have a very, very low mass, which means that as the black hole is rotating, the scalar hair co-rotates along. And there's a long-range dipole-dipole interaction that modifies the spin angular momentum of the system. And we'll see that. And then what's going to happen there is that modification of the spin angular momentum due to the long-range interaction is going to modify the phase of the gravitational wave amplitude of the emitted gravitational wave. And how does it do that? There's a correction to the phase due to the scalar here, and that is encoded in this case, chi is related to the scalar field amplitude. And so what happens is that this induces a spin. So if we look at this black hole, it has a spin, it has orbital angular momentum of the system. And what's going on is that this scalar here is going to basically modify the spin orbit and spin interaction of the unperturbed system, such that the phase information in the gravitational wave, emitted gravitational wave, gets shifted by this amount. And now the name of the game, not for me, but for the experts, is to figure out how to tease out this phase information in future observations. And there is a degeneracy between the parity violation and spin in black hole systems. And this is a 1 PN correction. Okay, so it's actually, a significant correction, but it is degenerate with non-Kerr modified spin in black hole systems. And people like Nico and his group and Franz Pretorius, and I'm sure some of you are thinking about, first of all, how to measure the spin of black hole binary systems directly, and also, if you can, how to tease out parity violation in this manner. So I want to leave you now with a movie of one way you might want to do this, which is that what you'd want to do is measure the spin of the system and subtract off this phase information. And that subtraction will lead basically to a beat. The same way, like, if I have two frequencies that are very similar, if I subtract it, I can actually know that subtraction by looking for a beat. And that's the kind of idea here. So what we're looking at here is basically a typical in spiral in the early phases for a few hundred times. So the blue is just basically pure GR. The red here, now this is in the in spiral, in the in spirals when the black holes merge. Can you actually hear anything?
I'm not sure we can hear anything from. We can hear you. I'm not sure we can hear much from the actual. There's a beat or anything like that.
Okay, what you were hearing is something that goes like whoop, that kind of thing, right?
I didn't get that. I don't know if anybody else did.
Okay, so let me see if I can do it again.
Yeah.
Okay.
Okay, so you got the sounds at the start, and then it sounded sort of went off halfway through. I don't know if it was meant to stop or if it was.
Okay, so that's, but the basic point is that what you're seeing here is to the upper right-hand side, how the frequency changes, and in the, the emergent phase, it goes up as the 7/8 law of the frequency. Okay. Now, what we're going to look at, the red now corresponds to Chern-Simons modified relativity. Okay. And by the way, I want to give thanks to Scott Perkins, who did the simulation. So the red and the red and the blue is Chern-Simons gravity is red, and you don't see much difference, right? Now this is actually when we get into the emergent phase. You can start seeing a phase shift. That phase shift is basically characterizing, still very tiny. You can see, well, it's something. But now if I subtract, what you should see is a beating phenomenon. And that's the thing that the people in the data game are going after. So this is a difference of the phase. And that's a beating phenomenon. So that would be a smoking gun signal of parity, how parity violation is encoded in Kerr black holes, if we were to be so lucky and advance to actually make such a detection. Thank you for your time. And I made it.
Well done, Stephon. Thanks very much. Great talk. So maybe now we open it up to questions. So David, do you want to take over sharing the questions?
Yeah, sure. Yeah, should we start with questions in A113 if there are any? Maybe Swaggart can unmute. And in the meantime, if anybody has a question online, just stick your hand up and we'll come to online afterwards. So A113.
I love questions, by the way.
Is somebody speaking in A13? I can hear you through the wall, but not through my speaker.
Dave, Thomas has got a question in the meantime, so if you want to just pass to Thomas while they sort themselves out.
Yeah, Thomas, do you want to go ahead?
Hi, Stephon. Thanks for the nice talk. Could I ask about, the very beginning when you were motivating the theory? I mean, the thought that crossed my mind is, if it's an effective theory, could I have terms in the action already that are parity violating? I mean, the action is constructed to be parity invariant, right? So your theta is a pseudoscalar.
Mm-hmm.
Could I consider the case where I have explicitly parity violating terms in the action already? Because I assume that there are some parity violations in the standard model, and then that they give rise to these terms at the effective field theory level.
Yes, you could. And I think that, the question here is that how different would it be from the typical solutions that Chern-Simons gravity will present? And I think it's useful to explore that.
I mean, what I have in mind is that if you could write down parity violating operators, you could couple the pseudoscalar with the Ricci scalar or whatever, with kind of lower order curvature invariance, and that could actually have an effect from the perspective of the EFT.
Yeah. So this was something that I knew very well many years ago, but there was an argument that I think Nico and I made, I think in our physics report. So there's a physics report on this where we considered what's the most general way to have a parity violating operator that's diff invariant and meets all the, and passes actually all the weak field limit tests of GR, PPN tests. And we found that Chern-Simons gravity was the best way to do it.
Okay.
There was a PPN analysis that was done as well. So that we wrote about.
Okay, thanks.
Yes, great question. Thank you.
Tony?
Yeah, so mine's kind of twofold, and I'll pick up on what Ali's put in the chat as well. So Ali's asking about going back to the smoke and gun signal. What threshold is required to make that a measurement? Is it something we could expect from LIGO, or do we need LISA? And I guess my question was related to that as well, which is this, would this signal be unique to Chern-Simons gravity, or are there other theories which may give something that look either very similar potentially?
I think in principle, there could be maybe a class of theories that would do a similar thing. But I think the name of the game is to go find those theories and compare it.
Okay.
Let me say it another way. It arises precisely because of the precise way that Chern-Simons gravity modifies the Kerr solution. So one will have to go back and go through all of that. That's my take on it, but it's a good question.
Okay, and as about whether the signal, what's the threshold? Obviously, presumably as you dial down the size of the coupling, then this is going to go away, right? So for typical values that we might expect motivated by fundamental theory, is this something that we're likely to see at LIGO or even LISA? What's the status of that?
Very good, very good. Well, to be frank and honest, the Chern-Simons coupling. So remember, what we have is an RR dual term, 1 over a mass scale in natural units, right? And then this field theta. So in this case, typically what we need is this thing to be this 1 over f, this decay constant, to be like very light, so like EV scale or less. And that's why we constructed this model from a UV, like a fermionic theory, right? To accommodate such types of theories. So that's the first, let's say, things that us theorists would like to hide under the rug, okay? You need this exceptional sort of EFT approach where this EFT is arising in the infrared, right? That's the first thing. And the second thing is that if you have such couplings or enhancements, there are other ways to enhance it in a nonlinear regime as well. That's just a linear statement I'm making that actually needs to be explored. And I would say that I'm not an expert. Nico certainly is the expert here. And what I'm hearing is that maybe advanced LIGO, definitely I would say LISA would be in the regime. But beyond that, and in a definitely supermassive case, that's the regime we're looking at, supermassive black holes. Those are the cases that was considered in the paper.
Okay.
And by the way, I did not write that paper. That was done by Kent, Yagi, and Nico. And some people, and Nico and I had a follow-up paper that was really pushed by those researchers.
I have another question, Dave, if nobody else has one.
Mm-hmm.
So I think in your initial slide, you alluded to a potential link to dark matter, but I don't think we got to discuss that at any point. But can you maybe just very quickly give a flavor of that, or did I remember wrongly? Was there a...
Yes, I mean, the idea of dark matter here is that, well, simply put, I mean, there's an axion there.
Right.
Right. So it also, naturally that comes with this is of something that's sort of like a mix between an axionic dark matter that kind of mixes in the gravitational sector as well. Mm-hmm. So it's kind of like a true dark matter in the sense that this axion is completely invisible, or could be, and it comes with it these parity violating gravitational sectors. Now, one thing that
in the correct range.
Say it again.
And the mass of this axion would be in the appropriate range for it to, for it to be a dark matter candidate.
It will be one of these ultralight axions.
Okay.
Now, let me just add something that just came to mind. One of the things that I think would be worth really thinking about here is how all these ideas fit in with the sequestering mechanism that you and Nemanja worked on. Yeah, there's some like resonances there.
Okay.
Stephon, can you hear?
Yeah.
Hi, Ed here. Thanks for your talk. So one of the problems that you can face if you have a theory that can explain at least 3 of the fundamental problems in cosmology is you've got 3 sets of independent data to fit to. And so I'm just wondering, what sort of constraint is it putting on this model when you want to get not just baryogenesis, you want to get the dark matter, and you want to get ideally an observable signal, unique signal with beats in it coming from LIGO.
Very good. So I would say that we need I would say for that to really work, and that's a real, like, I would say, okay, I'm being a bit of a salesman here, and I would say maybe too ambitious. I would say for all 3 of them, we would need basically multiple axions, something like an axiverse, with different decay constants, and the effects of the Chern-Simons occurring at these different epochs. That's one way of thinking about that. But if we were to pin ourselves down to one axion, I would say something in the mass range of, like, 10 to the 8, 10 to the 7 GeV could actually do leptogenesis and dark matter, but definitely not the black hole stuff. You need a much lower scale to actually get some kind of amplified signal in the black hole regime, at least to our knowledge. That's a great question.
Thanks very much, Stephon.
Oh, by the way, who's that question from? I didn't see a name there. See, A113.
Ed Copeland.
Hey, Ed, nice to see you again.
I'm
don't know where I am.
to that.
Oh, here.
One of my heroes in cosmology.
Thank you.
Okay, are there any other questions from A113 or online? Okay, if not, should we let's thank Stephon again for a very nice talk.
You guys, and come visit me. Come visit me in Providence. I look forward to seeing you all at a pub close by.
Thanks a lot.
Thanks very much.